Yeah. Okay. So am I audible and can you see the screen? Can someone comment? Can't hear you. Yeah. Okay, you can't unmute yourself. Okay. Let me just check what is happening. Uh, Meeting options. Yeah, now can you try now?
Yes,
Can
sir.
you try?
Good morning, sir. Yes, sir.
Okay, well, good. Okay, now we can proceed. So, my name is Sudheesh. I'll be taking modeling of wireless channels. Okay, I think you might have seen a little bit of a small version of this topic in Tanvisa's class. So we'll be seeing how channels will be modeled in this tutorial. Okay, let me see how many people are there. That means half are there, right? Should we wait?
Sir, it would be good if you could wait 5 minutes.
Okay. Yeah, so I think I can start. I don't think it is good to wait for more time. Okay, so as I said, the topic is modeling wireless channels. So regarding the references, the first reference that I would suggest is Wireless Communication by Andrea Goldsmith. And I think this is the same textbook that is suggested by Tanvir sir also, right? Yeah, so my comment regarding Andrea Goldsmith is that yes, we are referring to that, and we'll be suggesting you to refer Andrea Goldsmith. But having said that, the language is little tough. If you're a beginner in wireless communication, and if you're trying to understand wireless communication, reading Andrea Goldsmith is uh, maybe an issue. In that case, you can go for wireless communications by Rappaport, which I felt is I think the language that is used in Rappaport is comparatively simple, and which is used in many universities for teaching. Okay, and if you still don't like the language in Rappaport, you can go for lectures and textbook by Professor Aditya Jagannathan. And he is a professor in IIT Kanpur, and he has a lot of video lectures that are available in YouTube. Like a multiple series of video lectures are available, like advanced 3G 4G communication, and this is one series that is available in YouTube, and there are multiple series under different names, and the language is also simple, the presentation is also very simple. And he also has a textbook which is titled as Principles of Wireless Communication, which is also good. So one good thing with that textbook is that the materials, the slides or the notes that is used in the video lectures is also used in this particular textbook. So it is possible to map or understand the video lectures or the textbook. Okay, so that is the comment regarding the references. So that means first one, Andrea Goldsmith, then Rappaport. You can refer to Rappaport, and I think the PDF of Rappaport is also available. The ebook of Rappaport is also available, and then this thing, Aditya Jagannathan sir's lectures, video lectures, and textbook. Okay, so let's proceed. So why are we no before beginning? If you have any doubt, one important thing I can convey to you is that since this is recorded, you can one option is that you can also go back to the recorded video and you can see the lectures. And if you have any doubts, what you can do is you can ask at a later stage, in the sense that after completing the particular lecture series, so that I will not lose the flow of that lecturing. Okay, otherwise if you have a trouble in following the language, or if you have a trouble in following the lecture or the the writing style or something, you can directly ask. Okay, now why we require modeling of wireless channel? The answer is that it is for better understanding of the nature of wireless environment. So what is actually the wireless environment? We'll be having a transmitter right? We'll be having a transmitter and a receiver. Let us say that you have a mobile base station, and you know what a base station is, right? A cellular tower or base station, you call it by different names. So that you can namesake, you can call it as a transmitter, and you have a receiver, that is the mobile. So you don't know what is happening between the transmitter and the receiver. So for proper understanding, you need to understand the nature of the wireless environment. Then only you will be able to transmit and recover the message in a receiver properly. So understanding the nature of the channel or the environment is important. Okay, so and the second thing is that to analyze the performance, that is quantitatively analyze performance of wireless communication system. So we can say that it produces this much error, or the bit error rate or error of the error at the receiver is high or low. So we can say that we can analyze the performance of the wireless communication system. So depending on the performance analysis, we can do some measures to solve the issue and to improve the performance at the receiver, so that we can perfectly recover or improve the performance of the receiver. So first one is to understand the nature of the environment. Second is to analyze the performance. So third one is that deterministic channels are rarely available, right? So we cannot always say that the channel will be like this always, right? So we cannot say that this is the channel at time 1, at time 2 this is the channel, at time 3 this is the channel. We cannot say that. So the solution is to model the channel mathematically, right? So as you can see here, something. Yes, there's some difference between the screen that I used to take and this bar was not there. Anyway, we'll just proceed. So are you able to see the screen? Do you have any issue in seeing the slides or in hearing the voice?
No, sir.
Okay. Okay, then let's proceed. So as I have just suggested, why we need to model the channel is to understand the nature and to analyze the performance, and since the channel is not deterministic, it is not deterministic, we have to model the channel. So I said that there will be a transmitter and there is also a receiver. So in this figure, what we can see is that this is the transmitter and this is the receiver. Okay, so we have one transmitter here and one receiver here. So when the transmitter sends signal from the transmitter, let us say that it is sending one particular signal and it follows different paths, like this is path 1 and path 2, path 3, 4. So the signal from transmitter reaches receiver via different paths. So in this figure, there are 4 paths. Okay, so the signal from transmitter travels from transmitter to receiver via 4 different paths. And the reflections is because of different obstructions that are available in the environment. It may be a big tree, or it may be a small house, a factory, or a tower, or a wall. it can be anything. So the obstruction that is present in the environment causes n number of paths between transmitter and receiver. Okay, so this different path is called as multipath. Okay, so the different number of paths that is available between transmitter and receiver is called as multipath. So this is one important name in modeling the channel. So though it is a big lecture, I mean it may take some 9 to 10 hours to complete the entire scenario, entire lecture series. The essence of the lecture is multipath and the channel variation, the time variation of the channel. It's very simple. So one main subpart behind this channel modeling is the multipath, that is different paths that is existing between the transmitter and receiver, and this occurs because of the obstruction that is there in between transmitter and receiver. So as I said, it can be anything, like it can be tree or a small house, factory or a big tower, anything, right? And that is all about multipath. Now the channel also will vary since because of the change in location, and it can change because of the change in location of the transmitter, and it can change because of the change in location of the receiver. Let us say that you are receiving the signal from a car. Okay, you are receiving some signal from the car, and you have this receiver at the in a car. Okay, so at time one you will be having let us say three paths. Path one may be there, path two may be there, path three may be there at time one, right? So at time one you will be having at time one you may be having three paths because of position at time one. And let us say that vehicle is moving and you have reached another point in time 2, and the obstructions may be different since you have reached from this point to this point and the receiver is here at time 2. So the obstructions may be different. You may be having 2 or 3 trees as an obstruction, so there may be 5 paths or there may be 6 paths or 7. It can be n number of paths, right? So the change in location is also an important point in modeling the channel, and that is the second point. The third point is that since the receiver receives multiple signal from multiple paths, in the figure you are receiving signal from path 1, path 2, path 3 and path 4, and all the signals are getting added up at the receiver, right? So the signal can be constructively added or it may be subtracted also. So it can be constructive addition or destructive addition. Right. Hope you know what is meant by constructive and destructive addition. Is there any explanation or diagrammatic representation to understand what is meant by constructive addition or destructive addition? Do you understand what is meant by constructive or destructive addition?
Yes, sir.
Yeah, for yeah. So if you have let us say plus sign, like +1, which is received in path 1, and if you are receiving let us say +1 in path 2, it will be constructively added. But if you are receiving +1 and -1 in path 2, it will be destructively added and nothing will be received in the receiver. So first one may be called as the constructive addition and second one may be called as a destructive addition. Of course, you know that the signal is not binary at the receiver. It is analog in nature. It is not purely digital in nature at the receiver. So I'm just showing this +1 -1 thing to understand what is constructive and destructive addition. Okay. Now, third point is that if you look at the multipath diagram, that there is a transmitter is there, receiver is there, and there are four multipaths, four different paths, right? So there is some label associated with each path. Some are labeled as NLOS, and one particular path is labeled as LOS, right? One is labeled as LOS, and another is another, and all the other are labeled as NLOS. So what is meant by this LOS and NLOS? So LOS means, LOS refers to line of sight. Can someone say what is NLOS?
So it is non-line of sight, any reflection.
Yeah. So if there is no reflection, you can say that it is LOS. There is a direct link between transmitter and receiver, then that is called as LOS. And if the path taken is from a reflected obstruction, maybe a tree or a building, then in such case we call it as NLOS path. So you have LOS path and different NLOS path. No line of sight of sight. Yeah. So that is all about LOS and NLOS components. So in this path, how many LOS components and how many NLOS components are there?
So 3 NLOS and 1 LOS.
Yeah, and is it possible to have multiple LOS?
No, sir, by definition.
Yes. Yeah, so we have here one LOS and uh, one LOS and three non-line of sight components in this particular diagram. Okay, so we'll be seeing different names for different channels with LOS and NLOS, and the channel names are Rician channels, relay channel, which you will be seeing in the later stage. So one with LOS component is called as Rician channel, and one without LOS component, I mean the channel which has only an LOS component, is called as relay channel, and you'll see it in a later stage. Okay, now yeah, so you have the transmitter here and receiver, and different parts are also there. So the single pulse that is transmitted from the transmitter is propagated via different paths, that is path 1, path 2, path 3 and path 4, and it receives at the receiver with different amplitude and different delay, right? And it appears as a pulse train at the receiver. It appears as a pulse train at the receiver. And why? Because why? The reason is that there are multiple paths and the time taken for the travel for different paths is different. Let us say that the time is tau 1 here. Time taken for this travel is tau 1 and time taken for travel is tau 2. Time taken here is tau 3. So if you are transmitting one pulse here, this is the pulse that is transmitted, but it looks like this is the transmitter, but at the receiver it looks like something like this. So it may be like this, or so this there are four different paths. So this is because of the LOS path. Since LOS path requires lesser time, it reaches fastly at the receiver. So all the three other paths will need different time. Like let us say it reaches at tau 1 and the third component reaches at tau 2 and the fourth component reaches at tau 3, right? So you are transmitting a single pulse at the transmitter, but it is received at the receiver as a pulse train because of the difference in delay and the amplitude. So as you can see in this figure that I have drawn now, you can see that the amplitude are different. It is not same. And can you tell me the reason behind that?
Sir, because if you have to travel longer in the medium, almost certainly you'll be attenuated more. And then there might be something frequency selective attenuation also. So that also contributes.
How do you know about frequency attenuation, frequency selective attenuation? Has it been taught?
As it came up, sir, in communication networks.
Okay, okay, fine. So we don't have to consider frequency selective or frequency flat or all the other terms now. So the simple reason behind different amplitudes is that, let us say you have path 1, path 2, path 3, path 4. It is coming after reflection from a tree or building or some other flat or tower, whatever. So there is some loss due to this obstruction, right? So that is the reason behind amplitude variations. Okay, so usually LOS path will be having higher amplitude. Usually LOS path will be having higher amplitude compared to all the other paths because there is no way of path loss in that LOS component compared to the NLOS component, right? So the amplitude in LOS will be usually high. And if you can see that there is some example with the LOS component with lesser amplitude, I don't know, maybe there, I don't know. So usually if there is an LOS component, it will be having higher power, but all the other components will be having lesser power, lesser amplitude due to the reflective nature of the channel. And these, just a second. So all these are called as NLOS component, and all the different paths experience different amplitude. All the path experience different amplitude and delay. Okay, so all the paths experience different amplitude and delay and phase change, which we'll see in a while. But since it does not carry much information, we will slightly forget about the phase change and we will focus more on the amplitude and delay part for the time being. Okay, so the point that I have mentioned now is that transmitter transmits the pulse, a single pulse, like you have seen here, and it reaches the receiver as four different pulses, and each is having different amplitude and delay. Okay, the amplitude of all the four may be different and the delay will be different. So that's all about the variations in the channel. Now we'll see multipath delay spread. So the term associated with multipath is delay spread. Yes, yeah. So the term associated with multipath is delay spread. So as we have just seen, transmitter transmit the single pulse and it reaches the receiver at different time instants. So the time between arrival of first and last pulse is called as the delay spread. Okay, so transmitter transmit the single pulse, it reaches the receiver at different time instants, right? Let us say that it reaches It is very difficult to understand where the pointer is located. Yeah. So it reaches the receiver at, let us say, tau 1, tau 2, tau 3, or tau 4. So the difference between the first pulse and the last pulse is, I mean, the time difference between the first pulse and the last pulse is called as delay spread. And delay spread occurs because of, what is the reason behind delay spread? What is the reason behind delay spread?
So because all of the signals have to travel different lengths of paths, you have a different amount of time each signal will take.
Yes, that is a more elaborative way of explaining, but we can bring it to a technical term, that is multipath. So since there is a multipath, there is a delay spread. Okay, we can say it like that. So as I said, multipath is an important term that is present in the wireless communication subject. Okay, so because of multipath, we have delay spread, and delay spread is the time arrival difference between the first and the last pulse. So as you can see, there can be LOS component or NLOS component. So the signal can be received at the receiver due to LOS path or NLOS path. Okay. What this means is that there may be situation where there is no LOS path. So if there is only NLOS component, still the delay spread is the time difference between first and last pulse. So it is not necessary that the first component to reach at the receiver is using LOS. It can be, I mean, if there is no LOS path, the first component to reach at the receiver is because of the NLOS path. So clear? If there is no LOS path, the first component to reach at the receiver will be NLOS. Okay. So what is the significance? What will happen if the delay spread is less, and what will happen if the delay spread is high? So if the delay spread is less, we have very little time spreading in the received signal. So the spreading in the received signal is very little. But if the delay spread is high, we have substantial signal distortion. We have substantial signal distortion at the receiver. Okay, so high delay spread is not good for a communication system. Uh, that means for lesser delay spread, very little spreading is happening at the receiver. But if we have high delay spread, we have substantial signal distortion at the receiver. So now the question is, how can you say that the delay spread is less or high? So to say that it is less or high, you need to compare it with something, right? Then only you can say that yes, this is less or this is high. So that parameter is called as inverse of signal bandwidth. So delay spread is compared with inverse of signal bandwidth, and then we decide that delay spread is less or delay spread is high. Okay, is it clear? So when we have lesser delay spread, it's okay, and when we have higher delay spread, then it is a trouble. We face significant signal distortion at the receiver. So for comparison, we compare it with inverse of signal bandwidth, and we say that delay spread is less or high. So can you tell me the what do you call it? Whether this comparison is happening in a time domain or a frequency domain. Which is the domain in which we are comparing this delay spread? Anybody there? See, yeah, my question is that we cannot compare something in time domain with something in frequency domain, right? So you cannot compare T with F, that is frequency. You can compare something in same domain. You can compare something in time domain, or you can compare something in frequency domain. So which is the domain in which you are comparing delay spread?
Sir, is it frequency domain?
Yeah, any other answer?
Time domain.
Yeah, of course. If it is not frequency domain, it is time domain. Okay, there cannot be any other option, right? Okay, so it is time domain. And why is it time domain? You don't need bigger, um, atmospheric science to know that it is time domain. It's because it
Sir,
is inverse of signal
sir,
band.
sir, because it is, sir,
Yeah,
or sir, because the formula for the delay spread, it is basically distance upon the speed. Like when we calculated delay spread in the previous lectures, it was basically the NLOS, like x plus x dash minus L upon C. So the x plus x dash minus L was basically the distance and the C was the speed of light. So we could say, so sir, we could say that it's distance upon speed, which is
yes, yes, yes.
basically time.
Yes, since we have one way to look at that particular problem is that it is a delay spread, the definition of delay spread, that is a time difference between arrival of the first and last pulse. So you can easily get that it is a time domain. Another way to look at it is that it is compared with the inverse of signal bandwidth. Of course, signal bandwidth is something that is in frequency domain. See, bandwidth, of course, you say that in hertz. Let us say that it is 10 kilohertz or 1 megahertz or etc. etc. So that is in frequency domain. So inverse of frequency domain is what? Inverse of frequency domain is time domain. Okay, so in both way you can say that it is in time domain. So why I have asked this is yes. So this is in frequency. Sorry. This is in yes. So this is in time domain, and we'll see terms, similar terms in frequency domain. So there is an inverse component that is associated with delay spread, which we'll see in coming classes, and inverse of signal bandwidth. Inverse of signal bandwidth, of course, is the signal bandwidth. So some parameter is compared with signal bandwidth, and then we can say that there is a signal degradation or not. Okay, so that we'll see. So since this class is just about an introduction of channel modeling, we'll stop with multipath and what is multipath, what is time variation, etc., etc., and we'll see each in detail in mathematically. Yeah, so I think I have drawn the diagram earlier. So let us say that we have transmitter here and receiver here. So you are, yeah. So you are transmitting a pulse here. You are transmitting a pulse here at the transmitter, and it reaches the receiver. Let us say that we have path 1 and path 2 and path 3. So it reaches the receiver at three different times. So I am drawing this for a reference, just like a reference line. So if I am transmitting something here, that is at the transmitter, it reaches the receiver at let us consider this as tau 1, and it reaches receiver at tau 2, and I'll do one thing. I'll reduce the amplitude here. Since there is a delay, I think it is good to reduce the amplitude. So it reaches the receiver at tau 3. Okay, so this is the time axis. Yes. Yeah. So what it says is that we are transmitting a pulse at the transmitter, and the receiver receives it from different paths, that is path 1, path 2 and path 3, and all these things are added up at the receiver, right? So path 1 plus path 2 plus path 3 is happening at the receiver, and overall we are having this at the receiver, right? So though we are transmitting only one single pulse at the transmitter, we are having a pulse train at the receiver due to the multipath. Okay, so is it clear how it is happening, how the pulse train is being generated at the receiver? Is it clear?
Yes, sir.
Yeah. So the important thing to be noted is that each path is having one amplitude. Okay, amplitude is that is alpha 1 and tau 1, which is the delay, and alpha 2 is the amplitude that is corresponding to the path 2, and tau 2 is the delay that is corresponding to the path 2. Similarly, alpha 3 and tau 3, amplitude and delay, amplitude alpha 1 tau 1, alpha 2 tau 2, alpha 3 tau 3. So all these things are added up at the receiver. So you can say that it is alpha 1 which is happening after tau 1, then alpha 2 that is present after tau 2, then after tau 3, sorry, this is alpha 3. Yeah. Okay, so here is the pulse train that is present at the receiver because of three different paths. Okay. Now, as I have said earlier, we have seen one important portion of the wireless communication, that is wireless channel, that is multipath. Second is the time varying nature. Okay, one important classification is the multipath. Second is the time varying nature of the channel. So multipath was occurring because of the different paths, different obstruction that happened. But here the time varying nature is there because that either the transmitter or the receiver is moving. That is, the change in position of the transmitter or receiver is giving rise to the time varying nature of the channel, right? So to yeah, we'll see some diagrams, and before that the intuition is that the multipaths will change. So as I have shown earlier, see, we have seen here that when the receiver moves from this point to receive, yeah, where is the, yeah, receiver is here and it is moving from this point to this point at time t2, and we have seen that number of multipaths may be different at t1 and t2. So because of that multipaths will change. Number of multipaths and the amplitude and delay associated with the channel will be different at different time instance, right? So we can just see it diagrammatically. That is, as you can see, we have amplitude here. We can say that this is the amplitude which is mentioned using dBm. So this is the amplitude. Right now we can see it as an amplitude factor, and we have the time factor here. So this is the first, this is due to the first multipath. Okay, this one is due to the first multipath, second multipath, and third multipath. Okay, so at time 1 there are 3 paths that is present at the receiver. Is it clear? We are observing the signal at the receiver. We are observing the signal at the receiver, and we can say that 3 components arrives at the receiver at T1. 3 components are received at the receiver at time T1, right? And each component is shown here. This is component 1, this is component 1, this is component 2, and this is component 3. So there are 3 components, right? Is it clear? Is it clear how I have drawn the diagram? Are you understanding it?
Yes, sir.
Yeah. What I'll do is I'll just erase that diagram and I'll draw it again. Okay, I am not able to erase it. Okay. Yeah. So what it means is that we have we have we are observing the signal at the receiver. We are observing the signal at the receiver at time t1. Okay, at time t1, and at time t1 there are 3 different paths. Signal is received via 3 different paths. So we are drawing the first path like this. The signal received via the first path like this. That is, this is the amplitude alpha 1, which is received after tau 1, and then second path we are considering, and the amplitude corresponding to the second path is alpha 2, which is received after tau 2, and then third path, that is alpha 3, which is received after tau 3, right? So the axis is you can say that this is the amplitude axis, right? Or we can show it using dBm. This is the amplitude versus time graph, and we are observing that 3 signals are received. The signal is received via 3 different multipaths at the receiver. Okay, so what are we doing now? We are considering, we are observing the same diagram at time 2. Let us say that we are trying to plot the diagram at time 2. So you can see that when you plot the diagram, when you plot the the received signal at time 2, you can see that there is very little change compared to this diagram, right? So what is the difference here? This is the first one is the observation at time 1. First one is the observation at time 1. Second one is the observation at time 2. Right, we are observing the first diagram at time 1, and we are observing the second diagram at time 2, right? So the difference is very less. This is one case. And now we are considering another case. Let us consider that at time 2 we are having a different kind of amplitude and delay. Let us consider that we are having a different kind of amplitude. That is, let us consider that we have alpha 1 like this, and we have alpha 2 like this, and we have alpha 3 like this. Okay, so if you compare these two graphs, there is significant changes. That if you compare alpha 1, alpha 2, and alpha 3, and the alpha 1, alpha 2, alpha 3 here in the second diagram, there is significant changes. That means in case 2, the channel, then I mean there is a variation in the channel. In case 2, there is a variation in the channel. But if you see case 1, there is very little variation in the channel. Which means that, I mean, roughly speaking, we can say that the channel is not varying in case 1, but channel has, I mean, there is significant variation in case 2. Okay, so we can say that case 1 is having, I mean, case 1 can be mentioned as a slow. I mean, there is very, very little change that is happening in case 1, but at case 2, we can have fast channel variations. Okay, and we'll see this in detail in coming classes. Is it clear? Or should I explain it once more? Why don't you comment?
Sir, it is clear for me, but I was waiting if somebody else had something to say.
Yeah, can someone comment? Someone other than the first commenter.
It is clear, sir.
Yeah. Okay, so as I was saying, there are two different aspects that need to be addressed when we are commenting about wireless communication. One thing is multipath, right? One thing is multipath that we have just seen, that is because of different paths, different obstructions. Second thing happens because of the time varying nature. Time varying nature, that is, you observe something at T1 and then you observe something at T2, right? You're observing something at T1 and then you're observing something at T2. So if you compare what you are observing at T1 and T2, if you see very less variation, then we can say that the variation is very less and it is slow fading. See, if the variation between channel at T1 and T2 is very less, we can say that it is slow fading. But if you compare the channel at T1 and if you compare the channel at T2, and if you can see that there is a significant variation in alpha 1, alpha 2, alpha 3 and tau 1, tau 2, tau 3. So if you compare the first graph and case 2, you can see that there is a significant variation. So in that case, you can say that channel is varying fastly. So it is fast fading, right? So in first case it is slow fading and in second case it is fast fading. So these are the two important parameters. First one is multipath, second one is the time varying nature of the channel. So if you can understand this particular subdivision and how the channel is modeled using multipath and time varying nature, then I think we can say that okay, almost all the topics are clear. So as we have seen in the previous previous slide, there is a comparison between delay spread and inverse of signal bandwidth. So similarly, how can we say that uh, the channel is slow or fast? What is the parameter that we use to compare? slow fading and fast fading. So the parameter that we use is coherence time. Earlier we have used inverse of signal bandwidth, but now to analyze the time varying nature, what we use is the coherence time. So if the variation is less than, is happening lesser within the coherence time, then the variation is slow. And okay, forget about that. We'll see it in a very elaborated way in the upcoming slides. So just note that there are two different variations. One is the multipath, second one is the time varying nature. And in first one, it is because of the different obstructions, and second one is because of the movement of transmitter and receiver. And in first one, we are comparing delay spread with the inverse of signal bandwidth. Now here we are using coherence time as the comparison parameter here. Okay. Now there is another topic, that is narrowband versus wideband, that is being addressed in Andrea Goldsmith. So before commenting on narrowband and wideband, I must say that this topic is mentioned in Andrea Goldsmith, but I didn't see this much elaborated comment in Rappaport. So if you want to read about narrowband versus wideband, I think you have to go for Andrea Goldsmith, not Rappaport. Okay, so let us say that we have three multipaths, and here you can see in the diagram, that this is the transmitter and this is the receiver. So we have transmitter here and receiver here, and one LOS path is here. And how many LOS paths are there? Can someone say? How many LOS and how many NLOS?
Sir, one LOS and two NLOS.
Two NLOS. Yeah. Any other comments? Is it two LOS and one NLOS?
Two NLOS.
Two NLOS. Yeah. Fine. So as you can see in this diagram, you have three different paths that are received at the receiver because of one transmitted signal at the transmitter. Okay, and one is LOS and other two is due to the NLOS. Okay, so if two multipaths are resolvable, then we can say that it is wideband. And if two multipaths are not resolvable, then we say that it is narrowband. Okay, is it clear? So if you can see in the diagram, you can see in this diagram here. So if all the components are placed together, then we say that it is a narrowband. But if all the components are kept apart, if there is a significant distance between all the multipath components, then we can say that it is a wideband. Is it clear? So we have narrowband and wideband, and if two multipaths are resolvable, then we can say that it is a wideband. And if multipaths are non-resolvable, see, you can see in this diagram, in the first diagram, that all the components are together, packed together. We cannot see any separation between the blue bar and the green bar. There is no separation, right? So it is not separable or resolvable. It is not resolvable. You cannot take the blue bar and the green bar outside. You cannot separate it. So in that way, we can say that it is not resolvable, and in wideband is resolvable. So by definition, I mean, coming to the mathematics, two multipaths are resolvable only if the difference between them exceeds the inverse signal bandwidth. So you can see that the equation here, tau 1 minus tau 2, that means this one is the delay, or you can say delta tau, that is this separation. If separation is more than, I mean, if separation is more, then we can say that it is wideband. So what is the parameter that we use to compare? It is the inverse of signal bandwidth. So if the separation is more than inverse signal bandwidth, then we can say that it is resolvable. And if it is not resolvable, it is less than delta tau is less than 1 by signal bandwidth. Okay. So the idea here is that if the multipaths are not resolvable, then we'll have to consider multiple paths as a single path, right? In this first diagram, if you see the first diagram, three different bars are there, but we cannot separate different bars. So what you have to do is we have to consider it as a single path instead of three different paths. So amplitudes and phases are summed up, and because of that, we'll be observing fast variations in narrowband. Okay, so since the three blocks are non-separable, we have to add the amplitude and phases, and since there is an addition, we will be observing fast variations in narrowband, unlike in wideband. Is it clear? Did you understand? I mean, from a layman's perspective, a layman's point of view, if it is separable, if it is resolvable, it is wideband. If it is not resolvable, it is narrowband. Is that clear?
Yes,
Yes,
sir.
sir.
Yeah. So it is the same diagram, but we are, we are showing in a different way. So we can consider this as a narrowband. That is, there are multiple obstructions here. You can see, yeah, you can see that there are multiple obstructions. Obstruction 1 is there, 2 is here, 3 is here, and because of obstruction 1, one path is here, obstruction 2, path 2, obstruction 3, path 3. So there are three paths, but since the obstruction or the buildings are very close, the delay will be very less. The delay between each blocks will be very less. So we have to consider the three multipaths as one single path, as it is not resolvable, right? So mathematically, what we can do is that if tau 1 minus tau 2, if tau 1 minus tau 2 is less than 1 by inverse signal bandwidth, that is, if the idea behind this is that the if the delay is very less, if the delay between different components, tau 1 minus tau 2 or tau 2 minus tau 3 or whatever, if the delay is very less, the multipath must be treated as a single path. But if the delay is very high, if the delay tau 1 minus tau 2 or tau 2 minus tau 3, whatever, is very high, then different multipath components exist. If the delay is more than 1 by inverse bandwidth, then different multipath components exist. So based on this, we can say that there are two different classifications. One is narrowband, one is wideband. So if the components are separable or resolvable, then it is wideband, and if it is not resolvable, then it is narrowband. So Yeah. So I think you have seen this Doppler effect in Tanvisa's class. Have you seen this?
Yes, sir. It was there.
Yes, sir.
Yes. So I think this diagram and the derivation has been addressed by Tanvisa, but just keep in mind that we have one equation FD is equal to, that is Doppler frequency FD is equal to V cos theta by lambda, which is the Doppler frequency. And if the direction of travel, if the car is moving towards, then the total frequency is Fc plus Fd. You can see that Fd is getting added up with Fc. And if the direction is away, if the direction is away from the source, then it is Fc minus Fd. So there are two cases, Fc plus Fd, Fc minus Fd. So first one is the direction is towards, that is the car is moving towards the source, then it is Fc plus Fd. And if it is moving away from the source, then Fd is subtracted from Fd is subtracted from Fc. So yes, so that's all about Doppler effect. Now a small calculation. Can you solve this? Consider a vehicle moving at 60 miles per hour at an angle 30° with the line joining the base station. Compute the Doppler shift of the received signal at a carrier frequency of 1850 megahertz. So what you have to calculate is FD, right? FD you have to calculate. Will you do?
Yes, sir.
Yeah. Yes, any answer? Any comment?
So
So what is the first step? See, the parameter to find is FD. So what is FD? V cos theta by lambda, right? FD is V cos theta by lambda. So do we have everything that we need? Cos theta, theta we have. Then lambda we have FC is there, right? Then V. Do we have V? V it is in 60 miles per hour. So what you need to do is you have to convert that 60 miles per hour to kilometer per hour, then to meter per second, right? So what is how many kilometers are 1 mile? I mean, what is the conversion? 1 mile is equal to how many kilometers?
1.6, sir.
Yes, yes, yes. So 60 miles per hour is equal to 60 into 1.6. Then kilometer per hour, that is 1000 by 3600, that is 5 by 18. So overall you will be having 26.8 meter per second. You got this?
Yes,
Everyone?
sir.
Everyone?
Yes, sir.
Yeah. Okay, so now we know what is V. V is equal to 26.8 meter per second. Cos theta is cos 30. Lambda. What is lambda? How will you calculate lambda?
Sir, speed of light divided by frequency. I'm getting something like 16 centimeters, 16.2.
Yes, that means you need this 26.8 into cos 30 by lambda, that is C by F. C by F, right? So you'll have something like this. Okay, so what this means is that if the vehicle is moving away, you have to do FC plus FD, FC plus FD. Sorry, towards it is FC plus FD. If it is away, it is FC minus FD. So just that. Okay, now we will proceed. Or should I wait for someone who hasn't got the answer? Everyone got the answer?
Yeah, where are you?
Who's talking? I heard some noise.
Also, at around 12, you will stop your class also, right? Yeah, yeah. Once you come to log out of your class, now if mine gets over, then can you just log out? Like, can you leave?
Are you talking to me?
Now, hello?
Are you talking to me? Anyway, fine. See, if somebody wishes to talk, just consider that there are like 230 plus other students who are there in this group. Okay, now I think most of you have got the answer, and now I am proceeding. Now a little bit of mathematical stuff. Okay, so we have S of t, that is S of t is the transmitted signal, which is the band pass signal. Band pass signal means it is centered at a particular carrier frequency Fc. So transmitted signal S of t can be represented as real part of u of t into e raised to j 2 pi fct. So u of t is the low pass equivalent of s of t. S of t is the transmitted signal. U of t is the low pass equivalent of the transmitted signal, which is not band pass. Okay, so you got the difference, right? S of t is the band pass signal. U of t is not the band pass signal. It is the low pass equivalent. So alternately, you can write this equation as real part of u of t into cos 2 pi f c t minus imaginary part of u of t into sin 2 pi f c t. Now we know the transmitted signal s of t. So we can write the received signal that is at the receiver, that is r of t. R of t is equal to real part of sigma n equal to 0 to n of t alpha n of t u, yeah, again was, yeah, alpha n of t u t minus tau n, then into e raised to j 2 pi f c t minus tau n plus 5 dn. Okay, so can you tell me what is n here, capital N here? What is capital N here? I mean, what is the sigma? What is the meaning behind the sigma?
So basically, we have to add up the effects of all of the multipaths at the receiver side,
Yes,
and
yes,
n of
yes,
t indicates how the number of paths changes with time, if any.
yes, yes, yes. So this summation means that, see, in S of t, we are transmitting, I mean, we have just one signal. That is S of t, that is real part of u of t into e raised to j 2 pi f c t. And coming to the received signal, at the receiver, you are receiving via different paths, path 1, path 2, path 3, up to n. I mean, in this equation, it starts from 0. So 0, 1, 2, 3, up to n. So you are summing up all the different received signal via different paths. And keep in mind that each path will be having different amplitude. Each path will be having different amplitude, right? And different delays and phase changes, right? So I have mentioned that each path will be having different amplitude, different delay, and different phase change. So if you look at S of t for in the transmitted signal, you will not be seeing this amplitude part and delay part and the phase change. So S of t, after, I mean, if you incorporate n number of signals with amplitude, delay and phase, you will be having received signal R of t. Is it clear? How we are having, how we wrote R of t from S of t?
Yes, sir.
R of t, yeah, R of t is S of t, but we are summing up different components, and each component will be having different amplitude, different delay and different phase. Hope it is clear. Any doubt in this particular equation? I mean, this is the I mean, backbone of the channel model that we are going to lay. Is it clear? So just keep in mind that each path will be having different amplitude, different delay and different phase, and we are summing up n number of, I mean, n plus 1 number of paths, and zeroth path is LOS path, I mean, and all other paths are in LOS path. Is it clear? Yes or no?
Yes, sir.
I mean, are you afraid? Why are you not commenting? All the others, is it clear or not clear?
Yes, sir.
Yes, sir.
Yes. Okay, good. So we have the transmitter here. I mean, I'm just trying to picturize the whole scenario. We have the transmitter here, and we have the receiver here, and we have some scatterers here. Okay, so this one is path 1. We have path 1 here, path 2 here, and path 3 here. So the transmitted signal is received at the receiver via three different paths. Okay, so the signal is received at the receiver via three different paths, and each path will be having different amplitude, different delay, different phase. And for the time being, I'm talking about only the amplitude and the delay factor. That is for path 1 it is alpha 1 tau 1, path 2 it is alpha 2 tau 2, then path 3 alpha 3 and tau 3. Now we'll try to uh, write the equation of the received signal. Okay, and before writing the received signal, there is one assumption that we are assuming that the transmitter and receiver are static. That is, we are assuming that there is no movement by this transmitter or receiver. I mean, the signal is there at the receiver because of the multipath only. Okay, so having said that, we are writing the received signal R of t is equal to A1 u of t minus tau 1, a1 u of t minus tau 1 into e raised to j 2 pi f c t minus tau 1. See, I am using the subscript 1 to represent the first path. You can either use alpha 0, tau 0, etc. to represent that it is NLOS path. I mean, subscript is to identify that it is the first path. I mean, the idea is same. Now coming to the second path, it is alpha 2 u of t minus tau 2 e raised to j 2 pi f c t minus tau 2. I mean, in the third path it is alpha 3 u of t minus tau 3 again e raised to j 2 pi f c t minus tau 3. So these are the three different paths, and at the receiver we are adding different paths. That is, first path plus second path plus third path is present at the receiver. Is it clear how we are writing the received signal?
Yes, sir.
Okay, so a demo, I mean a pictorial representation of the same is given here. So let us say that you are having first signal at the transmitter and it is received after a delay at, this is the path 1 where you will be having delay tau 1, and there is an amplitude factor alpha 1, and similarly path 2 is there, which is delayed by tau 2 and amplitude is alpha 2. Similarly, this one is tau 3 and amplitude is alpha 3. Path 2 and path 3. So I think the significance of amplitude and the delay is clear in the mathematical sense and the pictorial sense. Now let us consider the same equation in two different scenarios, that is narrow band and wide band. So we have said that if the components are non-separable or non-resolvable, we have to consider the entire unit as narrow band, I mean as a single path. So here in the first equation we are considering narrow band, that is we have only one single path since the scatterers are placed together, and we have only one path here. But if you see the second diagram, there are three different paths. Alpha 1, path 1 is there, path 2, path 3. So there are three different paths which are resolvable, right? So there are three different paths, and these three paths get summed up to form R of t. So R of t is equal to alpha 1 u of t minus tau 1 e raised to j 2 pi f c t minus tau 1 again alpha 2 u of t minus tau 2 e raised to j 2 pi f c t minus tau 2, and it continues, right? So there are three components when it comes to wideband, and in narrowband, since the scatterers are placed together, we have only one component. Okay. Now it is the same equation for the received signal, that is R of t is equal to real part of, see, we have seen this equation here. We have seen this particular equation here, that is, yeah, see this equation, that is real part of summation of alpha n u t minus tau n e raised to j 2 pi f c t minus tau n plus the phase change. So the same equation is mentioned here, R of t, which is noted as equation 1. Then we substitute phi n is equal to 2 pi fc tau n minus phi dn. That means we are taking this part j, I mean sorry, 2 pi fc tau n and phi dn. This two parts we are taking and equating it to phi n, and phi n is clubbed back to equation 1 and we will get equation 3. So if you put equation 2 in equation 1, what we will get is R of t is equal to real part of multiparts, that is summation n equal to 0 to capital N alpha n e raised to minus j phi n u of t minus tau n into that up conversion part, that is e raised to j 2 pi fct. Okay, so this can also be represented using this particular equation, the last equation, that is equation 4, that is mentioned here, that is R of t is equal to real part of integral c into u of t minus tau d tau. So this particular equation is the convolution. That means whatever you are transmitting at the transmitter is convolved with the channel. So this one is the channel. Whatever you are transmitting at the transmitter, that is u of t, I mean this is the low pass equivalent of the transmitted signal, right, that we have just seen. So the low pass equivalent part is convolved with the channel to form the received signal. Okay, so that is how I mean our aim is to obtain what is channel. See, the aim of all this derivation etc is to understand what is the property of the channel. So from equation 3 and 4 we are trying to understand what is channel, what is c of t comma t, I mean tau comma t. Okay, so if you see this equation from equation 3 and 4, channel c of tau comma t can be written as summation n equal to 0 to n alpha n of t e raised to minus j phi n of t delta tau minus tau n of t. Okay, so there is amplitude factor here, delay here, sorry, phase change here, and delay here. So this is how we model channel. So the channel has the channel can be called as n tap channel. That means it is the presence of multi paths. We have n different multi paths coming into the picture, and each path will be having different amplitude, different delay, different phase change, and we can represent the channel using this equation, that is summation n equal to 0 to n alpha n e raised to minus j phi n delta tau minus tau n of t. Okay, so if you look at this equation, you can see that we are using delta here. See, we are using delta here, but in the previous equation of let us say equation 1, what is being used is u, right, because we had to incorporate the transmitted signal. This one represents the transmitted signal, but here it is the delta part. Delta is the impulse. Delta is the impulse which has the amplitude infinity at 0. So all the other time it is 0. If it is 0 plus, it is 0, and if it is 0 minus, it is 0. But at 0 the amplitude is infinity. So this is how you represent the channel. So channel can be modeled as C of tau minus t is equal to summation n equal to 0 to n alpha n of t e raised to minus j phi n of t delta tau minus tau n of t. So now you have the equation for the channel. So by understanding the amplitude, delay and phase of each path, we can model the channel. Okay, so now we have written that C of tau comma t. So what is meant by this tau and what is meant by this t? The idea is that we are, I mean, the measurement is taken at the receiver at time t. Signal is received at time t, but it is transmitted at a time tau time before t. It is transmitted tau units before t, right? It is transmitted before tau units of time before t. Is it clear? That means transmitted had transmitted it at a time t minus tau, and the receiver has received it at a time t, and observation is taken at this particular time. So that is why we are representing the channel as C of tau comma t. That means tau is also important and t is also important. So tau is the delay. How much delay is there between the transmitter and receiver, and t is the time at which we are taking the measurement. Okay, now what you're doing is we are clubbing that particular equation. I mean the equation for channel C of tau comma t back to the equation, back to this particular equation, back to equation 4, and we are making sure that we got r of t as in equation 1. If you can note that this was the first equation that we have started. Okay, and what you can see is that you can just have a look that there is one small property that we are using here to get equation 1, and it is called as shifting property. It is called as shifting property, that is integral delta tau minus tau n into u of t minus tau d tau, which is equal to delta t minus tau n convolution u of t is equal to u of t minus tau n. So this particular property is called as shifting property. So just keep this in mind. It is not shifting property. It is not shifting. It is not shifting. It is shifting property of the delta signal. So by using that simple property, we are getting back equation 1. We just have a look. Now having defined the channel, we'll just see how we are getting the received signal. So now what I'm trying to do is I have a transmitted signal which is something like this. So this is the transmitted signal, and this is the multipath channel, or we can say that this is C of tau comma t, what we have just defined. So this is, first one is the transmitted signal, and second one is the multipath channel, and you have to identify what is the received signal. What is the received signal? Please try. Let's see if you can come up with the answer or not. So how many parts are there?
There are three parts.
Three parts. So each path will be having one amplitude and one delay, right? So what is alpha 0 or alpha 1? Alpha 1, I mean the amplitude for the first path.
-1, sir.
Minus 1. Delay is
0.5.
0.5. And can someone say that what is alpha 2 and tau 2? Someone other than the present commenter.
1.5 and 1.
1.5 is the amplitude, right?
It's the amplitude. Yes.
And 1 is the delay. Yeah, okay. And for path 3, anyone else?
0.75 is alpha 3 and 1.75 is tau 3.
Tau. Okay. So let us take path 1. Let us take path 1. And what will happen if that signal is transmitted via path 1? What will happen? Anyone else? Can someone comment? No one? Then what is the meaning of whatever I have taught till now? See, there is a signal and you know the delay and amplitude. Why don't you mention the output? How will you draw it?
Sir, we will have u of t placed at 0.5 and inverted.
Yuvraj, I think you have answered already, right? Yeah,
Yes.
let someone else comment. Anyone else? Or are you afraid?
We'll have the amplitude -1 and the signal ranging between 0.5 to 1.5.
Amplitude -1. And when it starts,
Starts at 0.5
then it ends
and
at
1.5.
1.5. Yeah. Then path 2. Someone else. Path 2. What is the amplitude when it starts and when it ends? Okay, I'll do one thing. I'll select someone from the list. Hmm. Yeah, Anish Patnaik is here. Anish Patnaik, you there? Should I note that you are missing? Okay, Anirudh Vaidyanathan. What happened to you guys? Are you afraid of me? Huh? Anirudh Nair, you there?
Yes, sir.
Yeah, I know. Yeah. Okay, so you tell what will be happening in part 2.
Sir,
Okay, here is yeah.
it and
Hmm?
yeah. So,
Are you trying to convey that the connection is not good?
no, sir.
Yeah, then tell. Okay, I'll do one thing. So there are 3 parts, part 1, part 2, part 3. So the signal is delayed by zero point 0.5 at part 1, and at part 2 the delay tau 2 is 1. That means it starts at 1 and it ends at 2, and amplitude is 1.5, right? And for part 3 it starts at 1.75, ends at 2.75, and amplitude is 0.75, and all these 3 are to be summed up, and you'll get the answer as shown in the output. Is this clear?
Yes.
Okay, you may not clearly get this output without a graph, or I don't know. Yeah, yeah, I think it is possible. -1 plus 1.5. Yes, it's possible. Okay. Anyway, is it clear, or should I explain it? Anyone else who didn't understand all these things? Is it clear?
Yes, sir, it's clear.
Yeah. Okay, now let us say that you have 2 systems, system at T1 and system at T2. You have 2 diagrams, right? So the first one is having 3 paths, one LOS path and 2 NLOS path. And the second diagram has one LOS path and 2 NLOS path. Okay, so if you consider first diagram, the corresponding uh, channel can be drawn. Yes. Okay, so the diagram of channel 1 can be drawn like this. That is C of tau comma T1 can be drawn something like this. So the diagram has some name which is called as power delay profile. So this diagram is called as power delay profile. So if you have a power delay profile, you can understand how the channel behaves. So there are 3 components, 3 parts, tau 0, tau 1, tau 2. And for tau 0, you have alpha 0, phi 0, tau 0. And for tau 1, you have alpha 1, phi 1, tau 1. And for tau 2, you have alpha 2, phi 2, tau 2. So this one is the channel or the power delay profile corresponding to the first diagram. And the second diagram's power delay profile can be drawn as there are 2 paths, one LOS path and second NLOS path, and first one has alpha 0 dash, phi 0 dash, tau 0 dash. Second path has alpha 1 dash, phi 1 dash, tau 1 dash. Or rather than drawing the power delay profile, we can use the equations, that is C of tau comma T1 is equal to sum summation n equal to 0 to 2 alpha n e raised to minus j phi n delta tau minus tau n. And for second diagram, we have C of tau comma T2, which is equal to summation n equal to 0 to 1 alpha n dash amplitude, phase change, and delay. Okay, so this is how we represent the channel. You can either use the power delay profile or you can use the equation. So this is one beautiful diagram that is given in Rappaport textbook. That is this. If you just see from uh, this side, that is if you look like this, I mean from this angle, that is only you take a slice at t0. I mean you should not look at t1, t2, t3, etc. So if you're looking at just t0, you can see that there are multiple paths at tau 0, tau 1, tau 2, tau 3, tau 4, etc. etc. So at a different time, that is t1, the reflections will change, the amplitude, delay and phase will change, and at t2 it will change. So this is how we can represent a time varying channel, a time varying impulse response of the channel. Okay, so it is important to mention one property, that is linear time invariant, that is LTI channel. Okay, so what it means is that the delay tau, same delay tau imparts the same effect at all time. Okay, it means that the effect, the channel at T1 minus tau will be same as the channel at T2 minus tau. That means that this T1 or T2 or T3, it doesn't matter. I mean, when we are considering, when we are taking the measurement, that doesn't really matter. All that matter here is the tau value, right? See, when we have mentioned C of tau comma T, what was this? T is the time at which we were taking the measurement, right? This is the time at which we were taking the measurement at the receiver, and tau is the delay before, I mean tau units before the transmitter has sent some message. So tau is the delay between transmitter and receiver. So this tau is the really, I mean the real important player in this channel. It is not T1. So for such channels, we can say that those channels are time invariant, or we can say that it is LTI channel. In that case, instead of writing C of tau comma T, instead of writing channel as C of tau comma T, we can write the channel as C of tau. So here T really is not important. What is important is the delay. What is important is the delay between the transmitter and receiver. I mean, at what time we are taking the measurement doesn't really matter. The delay, the time delay between the transmitter and receiver is important here. So for an LTE channel, we can write C of tau as we can write C of tau as C of tau is equal to summation n equal to 0 to n alpha n e raised to minus j phi n delta tau minus tau n. So if you have seen this equation and the previous equation, the main difference here is that in previous equations we have considered effect of t. You can see here that t was, I mean, really important. Now we are not considering t much. I mean, we are not considering t at all. We considered the delay, not t. So C of tau is equal to summation n equal to 0 to capital N alpha n e raised to minus j phi n delta tau minus tau n. So for a continuum of multipath signals, continuum of multipath signal means narrowband channel. For a narrowband channel, what we can consider is that C of tau is equal to alpha tau e raised to minus j phi tau. That means we have only, here we have only one signal, right? Here we have only one path. If it is not narrowband or if it is wideband, we have the summation term. But for narrowband or for continuum of numerous multipath signals that are packed together, we have only one signal. So there is no need of summation part. Okay, now a small question. So consider a wireless LAN operating in a factory near a conveyor belt. The transmitter and receiver has a LOS path between them with alpha 0, phi 0, tau 0. Now, every t0 seconds, a metal item comes down the conveyor belt, creating an additional reflected signal path with gain alpha 1, phi 1, with parameters alpha 1, phi 1, tau 1. And what we have to do is we have to find the impulse response C of tau comma t. Can you look at the answer and just see if this makes sense? So it says that usually there is an LOS path, right? There is an LOS path which has the parameters alpha 0, phi 0 and delay tau 0. So the equation can be written as C of tau comma t is equal to the first part, this one, right? Usually we have an LOS path, that is alpha 0 e raised to j phi 0 delta of tau minus tau 0. So this is the general case. So what happens at every t0 seconds? So that means 1 into t0, 2 into t0, 3 into t0, 4 into t0, etc. etc. So every t0 seconds, another path is being generated. So there is path 1. There is another path that is being generated at every t0 second. So this is the extra path that is generated, that is alpha 1 e raised to j phi 1 delta tau minus tau, and this happens at every t0 seconds. Otherwise it is only a single path. Is it clear? When t is equal to n t0, that is every t0 seconds, for every t0 seconds we'll be having an additional path. Otherwise we'll be having only a single path, which is like this. So we have only one path here, but at t is equal to n t0 we'll be having two paths. Clear?
Yes, sir.
Yeah. Okay. So yes, so the effect of path delay, or we can say fading, is that we'll be having constructive or destructive addition at the receiver. So have you ever noticed that when you are inside some room or a hall, have you ever noticed that at some point you'll be having range, you can talk properly, or at some point you will not be able to talk properly? Have you experienced this? Yes or no?
Yes, sir.
Yes, sir.
Yeah. So the reason is that at some point, due to this multipaths, due to these multiple reflections, you will be having destructive additions and you will not be able to receive any signal, right? But if you change the position by like maybe 1 meter or 2 meter or etc., you will be able to have constructive addition, and then you will be able to talk properly. Right? It is not based on the distance. It is based on the addition of these multipath signals. Right? And it is called as small scale signal fading. And the significant fact is that if you consider Fc into tau n, which is greater than 1, then a small change in tau n will be having a bigger change in the phase. See, we have already seen that. For this idea, what we have to do is we have to consider this equation. Phi n is equal to 2 pi Fc tau n minus phi dn. There is some equation that we have substituted. See, we have substituted it here. Equation 2. Phi n is equal to 2 pi Fc tau n minus phi dn. Right? So, if you consider Fc into tau n, if this part is very high, if Fc into tau n is greater than 1, then a small change in tau n will bring a bigger change in the delay, right? A small change in Fc into tau n will bring a bigger change in delay, and then that may cause constructive or destructive addition. Okay, so if Fc into tau n is greater than 1, then a small change in this tau n can lead to a higher change, a larger phase change, which can cause a constructive or destructive addition. So I'll just go with one more slide and then I'll end. Okay, so regarding calculation of delay spread, see, we have seen delay spread in first slide, second, third slide, I guess, where we have mentioned power delay, multipath, right? Delay spread, the difference between the first path and the last path. Okay, so the equation for that is that the delay spread Tm is equal to max of tau n minus tau 0. Max of tau n minus tau 0. So if you consider like this, if you have multipaths tau 1 minus tau 0 or tau 2 minus tau 0 or tau 3 minus tau 0, what you have to do is you have to select the maximum value, and that is the delay spread. Okay. So if you look at this particular diagram, can you identify what is the delay spread?
Five microseconds.
Yes, so it's crystal clear. That is the difference between first path and last path. Last path is at 5 microsecond. First path is at 0 microsecond. So 5 minus 0, that is 5 microsecond. So the delay spread is 5 microseconds. Okay. Yeah, and so one more important point, and then I'll stop. So the idea is that we have delay spread for different channels, that is indoor channels, suburban channels, and urban channels. And typical delay spread for indoor channel is like 10 to 1000 nanosecond, and for suburban it is 20 to 2000 nanosecond, and for urban it is 1 to 30 microseconds. That is, it is high. So the reason behind this lower delay spread for indoor is that, see, the multipaths arrives faster. The distance is less in an indoor scenario. See, if you are holding a mobile in a particular hall, different paths will reach your mobile very fast, right? So the distance is very less. So the delay spread is very less. But in urban scenario, what happens is that due to numerous reflections, there may be it may take longer time to reach the, it may take a longer time for the last component to reach at the receiver. So delay spread may be high. Okay. So these are the typical values for delay spread for different scenarios. Yeah, and let's stop at this point.